Swayam Prabha. Digital India. Educated India.
Okay, dear students, today I will teach you the multiplex sensor that I started the last class. Let's continue this one. So there is lots of applications of multiplex sensors, not only on the just basic substrate on the I just taught you the ITO or some other plastic substrate we can use, but also this kind of multiplex sensor can be useful on a lateral flow basis. Means if we can use the paper based sensor like lateral flow based sensor, it can be useful for like many applications and it will be very cost effective and easily you can bring forward the point of care diagnosis. Let's show you this as the example. So mainly today's teaching main concept for this is the multiplex sensors on how we can use this concept for extreme point of care. And then its optimizations and design. I will show you the different design for lateral flow base. So main keywords, if you want to search this this teaching topic, mainly you have to think about the multiplex sensors. You can search and point of care diagnosis. Today's lecture is very much important for extreme point of care. See, here is the one image you can see here. You can easily predict like lateral flow. Lateral flow I already taught you. So like a paper strip we can use. There is a different chamber or region, right? One is this is called the sample pad or where we will drop the sample, and another is the reagent or different kind of conjugated agent we will use here. For if we need any chemical amplification, that we can use some reagent, or otherwise we can use some secondary antibody, that is label. With label, that is the reagent area, or you can say the conjugated area. So this is called sample pad where we will drop the sample, and this one conjugated pad or reagent pad, whatever. And another region we will use where we are actually getting the output. One is called the test region or test line. Here is the test line and another is the control line. So especially in the color, we will see the change of the color in the case of the lateral flow assay. So this is the colorimetric based biosensor. We will see the color change. So one is the test line, we see the T, we can mention T, and control line we are generally mentioning this one as a C. And rest of the part here we will use another pad that is called the absorbent pad. This one absorbent pad. So this pad why we need? This one like excess solution, excess like antibody. If you have the excess antibody, if they don't bind here, so they will be here, they may come and absorb. This is the absorbent pad. So what we will use in the sample pad, they will help to flow from, if you have some target, like if your sample content target, then it will from here it will flow, and their conjugated pad that already contain a secondary antibody that label with some any label we can use, but mainly for colorimetric sensor case we use here gold conjugated, because when gold conjugated secondary antibody come in the test region or control region, they will accumulate and they will show some reddish color that we can see. And based on this color, you can predict the target present or not. This is a very simple method and very useful method. The best example and best I think commercialized product that available in the market is a pregnancy test kit, similar like this. So you can add here the urine sample and if it contains the target, then you will see the color change the target, otherwise you will see only control change color, target change, you will not see any color change. Then you may ask, then why we need the control region? Only test region is fine. If you see color change, that's is okay, target present and no color, but why the need for the control then? Yes, it is also needed. In the control region, then you have to understand the mechanism. Test region, we are using one antibody that is specific for your target, and control region also we are using another antibody that can help to bind your all the secondary antibody that conjugated with secondary antibody that conjugated with gold nanoparticles. So, if you have target or not, anyway your secondary antibody that is conjugated with gold nanoparticle, they will come here, they will bind with this antibody and they will show the color. To validate your strip, means your strip is working fine or not, means it is, you can say the valid test, when your test is valid or not. If you see the control line is not also showing the color, it means your test strip is invalid, it is not working. So, you cannot use this strip. That is why control region you are getting color, it means your strip is working fine. See now how it is working. So, when you drop the sample, your target will bind with secondary antibody that already conjugated with gold nanoparticle. So, your target already bound, then it will come, then secondary antibody that is present some on your test zone, there it will bind together, and like this secondary antibody will bind, that is gold, this one in the test region, and because of so many gold nanoparticle will bind here, you will see the color. Same thing will happen in the control region also. Control region case what? You have the one antibody, secondary antibody here also another secondary antibody present, but here without target, only your secondary antibody that we use in this conjugated pad that is conjugated with gold nanoparticle, they will bind and will show the color. It is clear now, right? If target present, then only you can see the change of the color. Here the basic, I can now, I think I will remove this extra thing. Let us see. So, in the test region case, the main basic biosensor is like this, gold, okay. But in the control region, the main basic biosensor is this, so gold, right. So, here without target it can bind, here with target it will bind the secondary antibody that conjugate gold. This is the main mechanism. See, you can see here. So, if you see, now let us come this image to predict your answer. See, if you see the test line and control line, both it is showing the color, red color, it means it is the positive test. And if you see that your control region color, but your positive region no color, it means it is negative test. But if you see here, actually sometime means there can your strip can be invalid. Sometime maybe it is showing something irregular, or maybe your test region showing color, but control region not showing color. Then you cannot trust on your strip. Okay. So, then you have to throw this strip, you have to try something new strip, not this strip. Okay. Now, you can see some other example also we can try, means let us design something lateral flow based sensor that can be useful for predictions of your biomarker present or not. Here you can see, so here I am showing the another just design. And this is one design for lateral flow based sensor, and another design here I can see that is called competitive biosensor, or another sensor sandwich. So, this one I taught you, this is the sandwich sensor. Another thing I can tell you, that is the competitive. Competitive means on your test line you can use already some antigen you can bind, okay, and antigen it's already bind. See, your reporter, like secondary antibody is conjugated with some label, that is gold, suppose, and if you have target, then this one will bind with secondary antibody, and as your test region already you have the antigen, right, and this secondary antibody already conjugated with some antigen or target because your sample contained the target. So definitely it will cannot bind. There is some competition reaction, that's why it is called the competitive assay. There is a competitive reaction, so it will not bind here. Okay, and it can come, it can means it will not show any color here, but if you have your secondary antibody that is level that already present in the conjugated pad, but if you don't have target, then it will not bind, target will not bind here. So definitely it will come and bind on the your target that already present on your strip, then it will show some color. So this mechanism is called competitive mechanism, and the previously that I told, that is just some sandwich, that is non-competitive mechanism. Means I can summarize you by just if I can show you some basic example now. See, here maybe I can show you one. Let's see one here I can show you. See, this is your, okay, let's go back. So suppose this I am drawing a paper strip, this is a strip, lateral flow strip. Okay, so in this strip, here one, this is the test region, and here one, this is the control region. So test regions also, what you can do, you can immobilize your biomarker, that is you want to detect, that is your target, that you can immobilize before. So your test strip when manufacture, your test region already immobilize your target, target already immobilized. Okay, now when you drop your sample, if it has again the target, like this target is similar, right? So your conjugated pad that contain your level secondary antibody, so it will bind with your target, right? This will bind. So definitely this target and this target, there will be a competition, so it will not bind here, that's why. So in this case it will not bind, it will not show color. So it is called a competitive, that's why it is called, that's competitive assay, because there is a competition reaction, it is already present. But see, if you don't have target in your sample, suppose you don't have target, then this one will come and definitely it will bind here, it will show the color. So this is the opposite phenomena. And this is just a design you can use for your biosensor development, just for example. Okay, now let's show you, for example, a SARS-CoV-2. How we can use this one for SARS-CoV-2 detection, this same lateral flow design. Let's show you. You know, in the case of the SARS-CoV-2, generally we are using one thing is the IgG, this is your target can be IgM, these two we are mainly targeting. So in our blood sample, first IgM generating. When if we infected with SARS-CoV-2, at the very beginning for few days we will have the IgM. So if we want to do the early infections, we may go for the IgM detection instead of the IgG, because IgG come around after a week or sometime. So it later stage we are getting this IgG. So if you want to go, that's why early infections, let's go for the IgM. You can see here the symptoms, if it's present, then IgM first come, then IgM, IgG both may come around this region, and mainly after that, if this x-axis is the week, you can see then IgG only present, and the IgG will present finally, then IgM will be diminished. Okay, so we can make some strip, we can make a strip for COVID detection, maybe one for IgM, one for IgG. Then if we get the IgM at the very beginning, then we can think about yes, no IgG, then we can think about the infection, I mean it is early infections or the later stage infections. And if we get like IgM, IgG both, then it is midway, and if we get the IgG, no IgM, so it is late infection. But still, this antibody detection case, you just keep in mind, antibody sometime will not give much preference here for the SARS-CoV-2 detection case. Better let's go for the whole virus detection, because after when virus come, then slowly it will produce the IgM, IgG. Means early detection only possible if you can go for the whole virus detection. That's why there is so many report. Maybe I can teach you some more example after this class. Then if you go for the whole virus detection, there is so many impedance based. That's I already taught you, like level 3 impedance based detection that we can apply for whole virus detections. So if virus present, then we can see the impedance change. That will be much more easier to predict the early detection level. But still, IgG, IgM also can give you the information. So in this case, actually colorimetric, and but still you should have some level of this IgM, IgG in your blood. Then only we can go for this color change. See here, actually I can show you some example, and you can see the color change of this. See, in the sample pad, we are mainly going to detect your antibody, right? So it can be the IgG or IgM, and on your conjugation pad, it already we are using some gold COVID-19 antigen conjugate. Okay, so here some we are using the conjugation pad, as I told you, no. So different way we can design. It is the another design. So here what we use a gold COVID-19 that is already conjugated gold nanoparticle, some antigen COVID-19, and gold rabbit IgG, that is also we use the conjugated one, and this one you can see in this image, that is just for your control line test. So your anti-human IgM, IgG and anti-human IgG, this all for the control test we are using, and so this all the antibody we are using for test region and control region. Just we want to detect like IgM and IgG. So just I just mentioned this different like competitive assay, non-competitive assay, this different kind of design you can use for SARS-CoV-2 detections also. So if we see like accordingly we can see the color, if the IgM present or IgG present or only IgG present, like in this case like IgG positive, IgM positive, or IgM, IgG both positive, and in this case we can see the all are negative. So based on this we can get the lots of information about the COVID-19. So this is also definitely a impactful detection, but you have to keep in mind that this IgG, this kind of detections may come after some certain times of the infection. That's why people now thinking let's go for the whole virus detections. Okay, so this all the things is very much details we have in this reference. You can go through this, but this is just a diagram of this lateral flow based for the COVID, or if you use the very specific antibody for other disease detection, you can go for that viral disease detection or that bacterial disease detection, that different kind of disease detection. Means very specific antibody you can use, and we can go for those disease detections. It is very simple and it is very useful for point of care also, because see just a strip and just drop the sample and we can see the color, right? But why at the very early, if the viral dose, see if you want to go for the whole virus detection and viral dose is very low, that is the drawback of this kind of lateral flow assay. If this is very low case, then this number of gold nanoparticle they are accumulating on the test zone or control, basically the test zone. Control zone definitely see always the color. The test zone will be very faint color or maybe almost no color you can see, although you are infected. That's why if you want to go for a very ultra sensitive detection, that time it will not be much useful. This is the drawback for this. That's why if you want to go for very ultra sensitive detection, that time we have to use some electrochemical technique that I already told you at the very first class. Why electrochemistry or electrochemical sensor is much more important than other biosensor. So we cannot see some color change, but in the case of electrochemistry case, we can see the change of the signal because they are highly sensitive. Let's come. I will show you a lateral flow based electrochemical biosensor. See, this is a lateral flow based, just paper based strip. Here this is the sample pad, here is the substrate pad. So sample pad means where you will drop your sample. It can be your urine sample, saliva sample or blood sample, means invasive, non-invasive, what you prefer you can choose. And substrate pad here we need, because in the electrochemical sensor I taught you we may need to use electrochemical chemical redox cycling or electrochemical chemical redox cycling. I think you can remember the last few class before I taught you why we need this kind of redox cycling, to amplify the signal to background ratio, so that you can go for the ultra sensitive biosensor. So sensitive biosensor. So we need this kind of electrochemistry by electrochemical sensor related strip when we want to go for like femto level detections, like very low. You can see in this sample pad we can use like T-shape, some substrates, some ruthenium, hexamine. You can remember, like let's show you the schematic. Like this is the sandwich form that we want to make on your working electrode. Okay, so your working electrode contain your capture IgG that already, see your working electrode, this one that already conjugated with capture IgG that can detect like troponin I. Troponin I, a cancer biomarker that we want to detect. So your capture IgG will be very much specific for troponin I that we already conjugated on the working electrode. Now we need some chemical, like you can see this one. What is the redox cycling reaction we are using here? See here the electrochemistry, electrochemical, this one chemical, this one chemical, right? CCE. So this redox cycling is the ECC redox cycling, right? Redox cycling that you can remember last time I taught you. So that redox cycling I will use here to get the signal amplification, because in this paper based strip I wanted to detect very low level biomarker. So your secondary antibody that conjugated with some label, they have in this region. Now when you drop your sample, then your reagent will be dissolved and your secondary antibody also will go through this flow and it will come to your working electrode region, and this working electrode region already you have the capture IgG. So your secondary antibody that already conjugated some galactose, some enzyme, and it will bind with your target and it will form this kind of sandwich, this like a sandwich ELISA type. So this form will form on the working electrode. So that actually in this working electrode area actually I am showing in this like broad, you can see that here highlighted. Here we actually zoom in this one, and we are showing this all the reaction part on the working electrode. So after this, see here you have the working electrode, reference electrode, counter electrode. We can connect this one with the potentiostat. We can make a portable small potentiostat that we can connect. I mean after your when you add the strip, maybe there may be some waiting time because it will come. All the reagent will come to their working electrode, they will bind, they will have some reaction. So maybe you can give some 5 to 10 minute waiting time, right? During this waiting time, the reaction will happen and this binding will happen. Okay. So after this waiting time, then this all the electrode you can add to the portable potentiostat. On the potentiostat there will be a display, or via Bluetooth maybe you can transfer this data to your mobile phone. You can see on your mobile phone there will be app, you just turn on this app, you can see the data. That is the IoT enabled sensor. So that part I am not telling now, mainly I am telling the mechanism part here on the working electrode. So on the working electrode, when you wait for 5 to 10 minutes, then your T-shape will react with this substrate that we use, some ANGP substrate that react with the galactose and it will form the electroactive species. That will again react with the ruthenium 3 and then produce the ruthenium 2, and this ruthenium 2 actually electrochemically will be oxidized on the sensor surface. So, this chemistry I already taught you, just I am showing one more time, like ruthenium 3 we used. So, in this reagent pad you have to use ruthenium 3 and you have to use ANGP, this substrate, and you have to use TSAP. Okay. Then when your target present, if you present the target, then it will bind the galactose on that working electrode and it will produce this electroactive substrate, and this electroactive substrate will react with ruthenium 3, it will produce ruthenium 2, and this oxidized species then again react with the TSAP, and this cyclic reaction will be going on. So, because of this we will amplify the signal and we will get the high current. So, and excess one, like excess ruthenium, excess other reagent, they will come to the absorbent pad. That is why, see, and also you can use some little amount buffer also if you want to wash out all the excess reagent part or excess when that can cause the background current. If you can increase the background current, then you can optimize how much buffer you want. That also you can do. So, kind of you do not need extra washing step, right? Just you are dropping mainly sample and then we are waiting for some time, we are getting the data. This lateral flow based electrochemical sensor. That is why this is also kind of wash free, because you do not need separate washing. It is automatically inside is a washing actually. So, you do not need extra washing, that is why it is actually wash free. And this kind of electrochemical sensor also very portable, very simple, and you can see the data for on spot. So, that is why it is very much useful for point of care diagnosis. See, we just try to detect the troponin I and see here the different concentration of troponin I, almost 10 femtogram per ml we can detect. So, we can go for the ultra low detections also. From this calibration curve you can see that we can detect almost the femto level and very ultra sensitive this kind of sensor also we can design. I will show you one the actual real image here. You can see it looks like actually like this. Actually, this is all the schematic I am showing during this teaching, but let us show you the actual real image for this kind of lateral flow based electrochemical sensing. So, it looks like, see, this is a very simple paper based. We can connect, like you can see working counter reference we just connected, and you can see here we can drop the sample, then the sample go through, then the reactions will happen here in the working electrode, and then when we connect this on with a portable potentiostat, so we will see the data. That is shown and done. So, within 5 to 10 minutes you will get the value, we do not need extra washing step. That is the utility of this kind of sensor. So, how do we learn today? That lateral flow based multiplex biosensors also can be possible. This is just for only one detection troponin I, but we can go for like a multiple strip, we can go like that's I taught you, like working 1, working 2, then reference counter also we can design. So, then more than one target also we can detect on the lateral flow. So, we can go for multiplex sensors also on lateral flow, and this is kind of fully wash free because you do not need extra washing steps, you are not doing manually, right? This is washings actually happening, but it is inside because of the lateral flow, because of this flow actually helping to wash out all the excess reagents you are not doing manually. So, it is wash free and it is cost effective, made by paper, and also it is very user friendly, you can bring very near to the patient. So, this is bench to bedside application, very much useful and easy to use. That is why this kind of technique is very much useful for point of care diagnosis. Okay, that is all for today's lecture. This was teaching the lateral flow based not single detection, multiplex detection. So, next class again I will teach you similar kind of sensor applications for other advanced technique that can be useful for point of care diagnosis. Thank you, students.